Section 6.4 is integration with tables of integrals. In other words, integrating with known integrals or solved integrals. Um, so there are four kind of major steps to these. You need to determine the form of the integral that's under evaluation. So in other words, you know, maybe you need to do a little bit of algebraic manipulation just to make sure you'll be able to match it to an integral listed in a table of general integrals. So that's leading into step two. And then perform necessary substitutions. What you need to do is make sure that the integral you start with matches the table integral exactly. So either use a u substitution or whatever needs to be done in order for that to be the case. And then perform the evaluate the integral, then reverse the substitutions and simplify the result. So it may seem kind of simple, to just say to find an integral of something, and we're just going to look at the table and write down what that antiderivative is. It could be that easy in some cases, but generally we're going to have to use a u substitution to sort of finesse our integral that we're trying to evaluate into a form that fits the table. So that's the real skill of it, is being able to do that. So our first integral is the integral of x squared times square root 9 minus x squared dx. Keep in mind that this could be done with trig substitution. We could use x equals 3 sine theta and proceed from there, and likely we would find, we should be able to find our way through that. But since that's not the purpose of this section, what we'll do is have a look at what we're dealing with. We have x squared times square root of a squared minus x squared dx. So, or u squared times the square root of a squared minus u squared du. I don't think there's much we need to do in order to change the form of this. This should match some of the table integrals that we have, or at least one of the forms. So let's look for this highlighted form in the set of tables. And I've attached these tables at the end of the physical copy of the textbook, if you happen to have that. They're also in the e-text. If you look under the appendix, you should be able to find these tables of integrals. So we have a form square root of a squared minus u squared. That looks to be this block on the top of this page. So in ours was u squared times the square root of a squared, some number, minus u squared. That's exactly our form right here. So we'll take note of that. That's number 31 in the table. So we can cite that when we make our next step. Citing the table integral number is not necessary, but it's a nice practice to have so you can check your work later, or so anybody looking at your work knows what you did. And we see the result of that. We would copy this onto our problem in terms of u, or possibly x. And doing so, let's go back to that problem. And this one's really just a matter of copying things directly. We know that a is 3, since a squared is 9. We just took the positive square root of 9 here. And we filled in all the details. U is x and a is 3. And we're able to evaluate our integral with these, with this table of integrals directly. So let's have a look at another one. So we have the integral of arc sine of the square root of x dx. Now, this one wouldn't be so bad if it wasn't for that square root of x in the argument of arc sine. That requires perhaps a u substitution or a little bit extra thought. It's not just substitute square root of x everywhere there's an x for the integral of the arc sine of x. This is just an entirely different function altogether. So what we want to do is we want to convert this integral to something else that has arc sine of just u in it, or just an x somehow, or just a variable to raise to the first power instead of a square root of something. Otherwise, we won't have a table integral to help us with this, and it's not a straightforward integration beyond that. So let u be equal to x to the 1/2. That would be great. Then we'd have sine inverse of u. Now let's see if everything works out. So if that's the case, then du is 1/2 x to the negative 1/2, taking the derivative of that function, and that's dx. So when we solve for dx, we get 2 times x to the 1/2 du. We've divided both sides by this expression right here. So if we carry out the division of that carefully, you'll see that, yes, dx is equal to 2x to the 1/2 du. So now we plug that in, and we plug in u for the square root of x, and I know things are mixed. That doesn't look good. That's not anywhere we want to be, but let's try it for a moment to see if we can work it out and make things right. So we've got sine inverse of u times 2x to the 1/2 du, that's our dx. But what we realize is that u is equal to x to the 1/2. So this term right here is just u, right? So we can swap that out as that. So then u is equal to, so there's our factor of u, replacing x to the 1/2. This 2 is just a constant, so it's factored to the front of the integral, outside of it. And our form now, which is much more amenable to the table, is the integral of u times sine inverse of u du. Now let's go hunting on the table to see if we can find this thing somewhere. So we're looking for forms involving trig or inverse trig functions. That's down here at this bottom block. And we scan this, we see we've got sine inverse of u du, we've got u sine inverse of u du. That's perfect. That's exactly what we're looking for. So we'd copy this onto the work we've got on the previous page. I've already got it there, so I'll just scroll back to it. But we've got this from our table of integrals, and we'll scroll back over, and we'll plant that information right here. So there it is, copied onto our page. We had it exactly as we saw it in this integral on our table, and we've quoted or cited where we got it from, table number 90. And we can proceed from here. So we've kind of done the harder part, which was to manage the u substitution and clean this original integral up to get it to be something that matches a table entry. And from here, we just back out of our substitution. Remember that u is x to the 1/2. Anywhere we have a u squared, we'll be able to swap that out with, well, u squared is x. So just use that fact along the way. So the line below what we copied from the table of integrals looks like this. We have 2x minus 1 over 4 sine inverse of square root of x. Root x is u times square root of 1 minus x is 1 minus u squared over 4. And all of these are times 2, so we can cancel with those 4's in the denominator to get 2's in the denominators. And the result is what we see in the box below. So it's pretty straightforward. Again, the hardest part is to adjust this integral, the one we're given, through a u substitution so that it matches something that will fit on the table. Now, you might successfully adjust the integral you're given to another form, and there's a good possibility that you would adjust it to a form that's not on the table, which means you'd have to go back and try to adjust it to something more like what's on the table. It might help to bounce back and forth to see if you're near a certain type of integral, and to see if that'll help guide you. So for instance, had we looked at this and I had gone to the table, I might have said, looking at those inverse trig forms, I might have looked at it and said, this is our near integral. Let's use a u substitution with u equal to square root of x and see what happens. And in fact, I suspected that the very first time I did this problem, but as I moved along and found that x to the 1/2 factor that came out, I kind of saw that this one might be useful. So then I steered my work to put things in that direction. So keeping an eye on the table as you adjust things is always very helpful. So one last one is this complicated looking thing right here. We've got the integral of secant squared theta times tangent squared theta over square root of 9 minus tangent squared theta d theta. So something suspicious about this form is all the structure we've got here. Things squared and then square root of a binomial, which is sort of the difference of squares in there. This thing reeks of an algebraic structure with trig functions in it. So let's sort of tease that out. So if we let u be equal to tangent theta, I'm focusing on down here. Then I'd have something like 9 minus u squared right? And that could be off to a good start. Let's see what happens to the rest of things. So if u is equal to tangent theta, then du is secant squared theta d theta. It's just by the derivative of tangent theta. Now, that means d theta is du over secant squared theta. Or we might see it this way. Secant squared theta d theta is du. So these two terms in our integral, we can write them next to each other, and we can replace them by du in the next line of our integral when we re-express this. Okay, so that's du, secant squared theta d theta. So we've gotten rid of the secant squared theta in the numerator and d theta. Now what's that tangent squared theta? Well, that's pretty straightforward. U is tangent theta. So tangent squared theta is this u squared in the numerator. Then underneath, we've got the square root of 9 minus u squared. Again, u is tangent theta, so tangent squared theta is u squared. So now we've got a form that might match the table. It's an a squared minus u squared form. So let's see if we can find this integral in the table. Again, this one might be amenable to trig substitution, and it probably is. But the point of this section is to use these tables and to reduce our workload when we're trying to work through more complicated problems. So let's scroll over to the table. We have a squared minus u squared forms. Not on this page, but on this page at the top, upper block, a squared minus u squared, square root of that. And now we scroll down, we had u squared over the square root of a squared minus u squared. So there it is. And we'd copy this form beneath our integral on the other page that we're working on. I've already got it written there. So we'll scroll back and we'll cite table number 34. We've got that written off to the side here, table 34. Here's that form that we just saw on the table. And we can work forward from here. Remember, we did have a substitution. Everywhere there's a u, we need to replace that u with a tangent theta. And that's exactly what we'll see carried out here. So there's that u is tangent theta. This is 9 minus u squared, 9 minus tangent squared theta. The u over 3 here is tangent theta over 3. And we can close this up as is. Notice in a lot of cases, sine inverse of another trig function could be simplified. This is a pretty complicated expression we've got over here on the right. This is okay to leave as is. That would be not a half angle identity, but a third angle identity, and we could probably derive something like that, but it would be an extension of trigonometry that we already know, so we're just going to leave that alone. So this is perfectly sufficient as is. So that's it for 6.4. There aren't a lot of homework exercises involving this, but remember that the crux of this method is to be able to manipulate your given integral to match a table integral, and that's usually through a fairly tricky substitution of some form. Using u as your variable at the very least might help you to match the table in a more visually appealing way. And you want to keep an eye on the table too as you try to adjust the integral that you're given, because it might guide you from an initial idea to a more correct idea in some cases.